Yes, I do. Sorry. 1 second. What happens? So we are actually live streaming.
An exam, but on Monday, we have a in-class lab activity. It's going to be the entropy lab, but I'd like as many people as possible to attend in person because it's going to be a whole lot easier and you won't have to assemble the materials needed for the lab. I sent an email out with information on what materials you'd have to gather if you have to do the lab at home, but it'd be far easier to do it in class and also a lot easier to exchange information. Because again, like last time, we're going to have people in the class take data and we're going to pool the data for a little bit of a quick analysis during class. So I'd like to start off today with this question. Can we move that to the side so everybody could read the text? Basically, why does warm air rise? And do you remember the discussion about the average separation of molecules in air at room temperature, their average speed, and which was over 1,000 kilometers an hour, and their mean free path, basically the distance that they would travel between collisions on average. So with that in mind, why does warm air rise? Got three possible explanations here. In that individual hot air molecules are moving faster than the cool ones, and so we're able to shoot up higher in the atmosphere. Or B, the individual hot air molecules find it difficult to penetrate the denser air below than the less dense air above. Or C, you can't talk about the motion of individual molecules. They don't tend to rise, but you can talk about that with very large numbers of hot molecules. They tend to rise as a group. So think about this for a bit. And
Your bird stop.
sorry?
Your bird stop.
I'll get to him.
Okay.
So why does warm air rise? Okay, anybody need more time? Show me your cards then. Okay, what's it look like on the chat?
Unanimously B.
Unanimously B. Okay, that's not the case here in the classroom. Nobody anywhere chose A though. And let's just eliminate that because that's not a correct explanation. Could I get a volunteer though to defend B?
I can. Can anyone hear me?
Unmute and speak up.
Sorry, can anyone hear me? Okay, sorry. So I chose B because
So what happened?
when air
not on?
gets hotter,
Well, it's on,
it's
but
less
sometimes
dense.
it does this thing where we have to test the speed.
Okay, I'll wait a second.
Okay, I can hear somebody now. Somebody go ahead and speak
Okay.
up.
This is Corinne Brunger.
Okay.
So I chose B because when air gets hotter, it gets less dense, which causes it to travel upward. And so that's basically why warm air rises.
Well, I don't see why that distinguishes B and C. Are you defending C?
I was defending B.
Okay. So can you comment on the behavior of individual molecules then?
Yeah, I guess so. Just because, when air gets hotter, the molecules tend to separate and the air gets less dense than cold air.
And so the idea behind B is that hot molecules find it more difficult to penetrate dense air that's below them as opposed to less dense air that's above them?
Yeah.
Okay. Does anyone else want to add anything to the defense of B? Can I get a volunteer to defend C, please? Go ahead.
I picked C because I think the reason that hot air molecules go up is because when they get hot as a group, their tendency is to increase their volume, which decreases their density, and things that are less dense in a fluid will move upwards because of buoyancy.
Okay, so you can't really talk about individual molecules. You have to talk about groups of molecules because why?
Basically because an individual molecule doesn't really have concerns of volume or density. Only as a group can you compare the density of air molecules.
Okay, so density really is meaningless when you talk about the behavior of individual molecules. You have to talk about large groups of molecules before you can talk about density. Okay, so we've heard some defenses. How about a quick exchange of thoughts? We had kind of a difference. We had more people that were in class choosing C and more people online choosing B.
You've heard my argument.
Do we have anyone commenting on the chat?
Nothing yet. Oh, there's one. You want me to read it out?
Please, loudly.
I guess the big thing we need to know is if molecules stick together as they rise or if they separate.
We're not having chemical reactions occur in our atmosphere very often, so ignore chemical reactions. But collisions are quite important. Remember, molecules travel, only, less than 100 nanometers before they collide. And during a collision, they transfer energy and momentum, and their speed changes dramatically. So you could have a fast molecule that basically nanoseconds later, after a collision, is now a slow molecule, and then another nanosecond after that is now a fast molecule. So pretty much molecules, you can only talk about them being fast or slow between these collisions. And these collisions are very frequent, and the molecules don't go very far, again, on the order of tens of nanometers between collisions. And their average speed between collisions is on the order of 1,000 kilometers an hour. That's more than 10 times the maximum speed of a Mini Cooper. Is that another comment that showed up?
Don't molecules move faster when they get hot and slower when they get colder?
Well, we talk about heat as being a kinetic energy on the molecular scale. So you can't talk about a molecule being hot so much as a molecule having a certain speed at a certain instant. And you can talk about an average speed if you consider a huge number of molecules. And only when you talk about billions and billions and billions of molecules can you talk about a group being either warm or cold. But you can talk about individual molecules at any instant, either having a high or a low kinetic energy. But the average kinetic energy is something that's pretty much uniform over an area depending on the temperature. So we can talk about an average over huge numbers of molecules, and that's related to the temperature.
So the real question is if hot air travels together or in separately individual molecules.
Okay, folks, let's show me what you're thinking now. Go ahead and weigh in on either B or C. either with cards or hitting one of those letters on a chat. Do you have a consensus?
Uniform C.
Okay, yeah, I was a bit leading in there. C is the correct answer. Again, you can only talk about the behavior of rising or falling if you talk about huge. We're talking about billions and billions and billions of molecules at a time. Will you even notice a large group of them either rising or falling? Because on the average, a huge volume, or not volume, but a huge amount of molecules, you can then talk about the group having a density. You can't talk about densities if you're talking about individual molecules. And really, you can't talk about a molecule being hot or cold, except that, you know, what its temperature would be. You can talk about if a whole bunch of molecules had that speed, what would be the temperature of that gas? That's actually a pretty useful thing to think about. But usually we just talk about, if you're talking about individual molecule, what's important is its speed and direction at any instant. And the fact that these collisions happen very, very frequently, the molecules really don't go in very far, and they pretty much lose all memory of their speed before a collision once they collide with something. Okay, let's go ahead and go to the next question. These are ones that I had hoped to get to yesterday, but got distracted. So here's one for Pocatello. We often get this fog layer over the town. It used to be a lot worse when we had a lot of trains. And you'd see something quite interesting when people had a lot of fireplaces going. The smoke from their chimneys would rise and then hit the top of this layer and then spread out in a blanket with air from the smoke from the chimneys just not rising farther than the top of this layer where you have this fog. And the question is, if you hiked up into the hills around town above this blanket, what would be the temperature? Would it be warmer than in the valley, colder, or could you in fact not predict? So there's reasoning for this, but if you have your personal experience, that's probably valid too. So think about this for a bit. Cooler, warmer, or cannot predict. Anybody need more time? If you're on chat, just do the Bilbo Baggins thing and type in time. Okay, show me your cards. A, B, or C. What's it look like on chat?
Mostly B, 1C.
Okay, we've got A's, B's, and C's then. Can I get a volunteer for somebody to defend A, that it's going to be cooler above this, this fog layer? Anyone? How about B? Can someone defend why it should be warmer?
I could try.
You do.
Josh Crossgrove.
So I thought it would be warmer up above because all that warm air that's sitting above the valley is keeping all the cold, foggier air down in the valley. And even once the chimney smoke rises, which is warmer than everything in the valley, once it hits a certain height and then disperses, that level is basically warmer than what the chimney smoke was as well. So that's why it disperses at that level.
Okay, so the smoke, while it's warmer than the air it was rising through, once it hits that blanket of warm air, it doesn't rise anymore because in fact it's more dense than the air above it. Okay, could I get a volunteer to defend C? How many folks chose B?
Pretty much everybody on chat chose B. There was only 1C.
Okay. Well, it's pretty much unanimous And then we had pretty much one person choose A, one person choose C, and everybody chose B. So I don't think we really need to talk about this. B, in fact, is the correct answer. And basically warm air rises. And in the case of fog, what we have is called an inversion layer. That's what this is called. And it's called inversion because normally you've got, well, it's where you got this temperature inversion. And you'll find as you go into the valley, in fact, one of my friends is a firefighter. And when the air is really, really still, you'll often get the cold air settling in the valleys, and the ridges will warm up a lot faster, and you can get these inversion layers too. And it can be very, very nasty if there's a lot of smoke from fires. Okay, I forgot, what was the next question? The next slide. Okay, yeah, we'll talk about that later. Okay, so I'd like to talk about phase changes. And we talked about there being lots of different states of matter, in that the ones that we have more common experience with, solid, liquid, gas, and plasma, but there's over 27 states of matter depending on how you want to count. But we always have these phase changes where if you add energy to a system, it's a phase change if in response to the addition of that energy, the temperature doesn't change, you just convert more of the material from one phase of matter to another. And you see this with water quite easily. And the book has a little bit of a graph. And thinking of it another way, if we look at temperature versus time, where we add heat at a constant rate to a material, say that's initially solid, well, you'll see that temperature, that solid rise until it gets to the melting point. And then as you add more and more energy, or as time goes on, you're not going to see a change in temperature, but you're just going to see more of the material change from the solid phase to the liquid phase. And once it's all liquid, then you'll start to see the temperature rise again. And then when you reach the boiling point, you're not going to see a change in temperature again. Any additional energy you add is going to turn more of that liquid into a gas. And once all the liquid is gone, then you'll start to see the temperature of the gas rise. And there'll be a similar plateau on the scale, I couldn't put it on, where you reach the temperature where the gas starts turning into a plasma. And then again, you'll see pretty much a constant temperature as you add more and more heat, as you turn more and more of that gas into a plasma. And then only when you have no more gas will you see an increase in temperature of the plasma. But we can add energy in other ways. We can do it by applying magnetic fields. We can do it by applying electric fields. We can even do it by increasing the pressure, adding energy by squishing the material, doing work by compressing it. And this can cause a number of different phase changes. For example, ice has many different solid phases where it actually goes into different crystalline structures as we change the pressure. As we compress it, once we reach a pressure where we'll get this phase change, we won't see that work we're doing in compressing it changing its temperature anymore. We'll just have a reconfiguration of the solid to a different structure. And then once everything is in that structure, then we'll start to see a temperature change as we squish it even more. So there's lots of different phases of matter, depending on the material. We could have quantum phases. We can have magnetization phases. But the ones that are more common are, at least in our experience, are solid, liquid, gas, and plasma. But we have no clue of the different phases of matter of what could be the case with dark matter. So there's still a whole bunch that we don't know. And let's see, I've got a bunch of demos that are kind of fun to share. I have in this drum, well, a bag of dry ice. Dry ice is carbon dioxide. And let's see. Colton, can I get you to light all those candles? You like the candles? Yes, all the candles. So dry ice or carbon dioxide does not exist as a liquid at atmospheric pressure. You'd have to increase the pressure quite a bit to have this turn as a liquid. And as a solid, it's pretty cold. The sublimation temperature. Basically, where dry ice carbon dioxide goes from a solid to a gas is, oh, what is it, about minus 60 Celsius. So it's pretty cold. And this is about room temperature now in this bucket. So we've got room temperature carbon dioxide, and it's colorless, odorless. Can't see anything in here, but this is a gas. And it turns out it's more dense than oxygen, than the air around us. And fire needs what gas to burn? Anyone? Somebody speak up online. What gas does fire need to burn? What gas do we need for our respiration?
Oh, you got a comment.
Anything online?
Oxygen.
What is that?
That was crystal sheath.
What was that?
Crystal sheaths.
Okay, speak louder when you talk, please. Okay, so yeah, it needs oxygen. And carbon dioxide is a lot more dense than oxygen. So if I were to pour this on here, the carbon dioxide is heavier and it pushes all the air, the other air in the atmosphere away from it. And so the candles are left without oxygen near them. And so they go out. That's why we use carbon dioxide in fire extinguishers. And in a fire extinguisher, what you have is you have liquid carbon dioxide, and again, it has to be a higher pressure. And when you hit the valve on the fire extinguisher, you then expose part of that liquid to atmospheric pressure and immediately goes into the gas phase. And it comes out as a result quite cold, even though the carbon dioxide liquid might have been at close to room temperature. By expanding like that, it gets very, very cold. Anytime you get a gas forcing to expand, you're going to see a drop in temperature. And so the temperature helps with a fire, but more so, it just pushes, since it's so dense, it pushes all the oxygen away from a flame. But gas takes up a whole lot more space than a liquid does. And I'm going to start something here that might take a while. I'm going to break off, some chips of this carbon dioxide, and I'm going to put them in a balloon. And so this carbon dioxide will turn from a solid into a gas, and the gas takes up a whole lot more space, a whole lot less dense than the solid. So I have several chips of dry ice now in this balloon. I'm going to squish it so that we have no more air inside the balloon, no more gas. Then I'm going to tie it off so that the solid that's in here, the gas that it produces, that it changes into, will not escape. And already we see that we have a measurable amount of gas in there. And we'll just sit this down and let it warm up. Probably, actually, is it in view of the owl camera that's sitting there?
It can be.
Okay, well, I'll just let it sit there. Or maybe let's put it over here on this table for some of the other demonstrations. Okay. I also have some more of that liquid nitrogen in here. Again, this is very cold stuff. And to show you how cold, I've got some flowers.
Oh my.
And if I make the flowers really, really cold, well, their behavior will be a bit different. I've got some other things I can cool down. I've got a racquetball. Let's get it really cold. And I've got a super ball. Bounces pretty well. Let's see how well it bounces when it gets really cold. And
Rubber band.
I have some rubber bands. But I think my flower is cold enough now. And these flowers, oh, they smell nice. The cold flower, I can't smell at all. When things get really, really cold, they often behave like a glass. And to demonstrate that, is there a way to turn up your microphones? If you're at home,
Give me 1 second.
So I think that they're fine if they just turn off the ones at home. Did you hear that? It kind of tinkled like broken glass. So it gets very, very brittle and quite fragile. And this is another reason I like the large basin. It's hard to fit the stretched rubber band in here, Braden.
Okay.
So, but I'm going to try it. Okay. So I stretched the rubber band out and froze it, so it's kind of stiff. Rubber is a long chain molecule, and when it thaws a molecule at a time. So some of them are going to thaw and try to contract, while other molecules are still frozen and rigid. So it does kind of a squiggle motion, and far more dramatic if I could have it stretched out more, which I can't do with the size of the vessel I have here. But let's see. I do have the Super Ball. It's not bouncing very well. In fact, definitely different bounce. What does that sound like?
Sounds like a marble.
Sounds like a marble. Well, again, a lot of materials behave like a glass when they get cold. So this behaves like a solid ball of glass or a marble. And as it warms up, it's actually less elastic and it doesn't bounce nearly as well. Okay, the racquetball, however, is hollow. It's not like a solid ball. So will the racquetball bounce really well like a marble or a super ball? What else is made of glass and is hollow?
A vase.
Or super ball or Christmas ornaments? So do you think this will bounce really well? Let's find out. No, did not bounce. It's shattered, kind of like a light bulb or a Christmas ball. And you see it's hollow. And did you hear a pop when it hit the ground? Well, the air inside that super ball got very, very cold. So cold, in fact, that it turned into a liquid. Liquid takes up a lot less space than a gas. So we had close to a vacuum inside the racquetball. So it really was kind of like a light bulb. And that's why it popped. So I've got some balloons here that are kind of clear. And if we make a gas really, really cold, what happens to its density? Anyone? What happens to the density of air if it gets really, really cold?
It increases.
Yes, it increases quite a bit. It gets more dense, it contracts. Same gas taking up less space is more dense. So this is quite cold. Again, this is minus 320 Fahrenheit or minus 196 Celsius. So watch to see if you can see a noticeable change in the volume of this balloon as it gets cold. Is it smaller than it was before? How about now? If I make it cold enough, in fact, all the air inside this balloon will turn into a liquid. And liquid takes up a lot less space than a gas. And I'm going to bring this really close to the laptop camera. If you look at this, you can see some liquid sloshing around the bottom of the balloon. That's liquid air. It looks kind of white and milky because it's mixed in with basically some water from the breath of whoever blew these up. And that turned into kind of a snow. And now we have a fog inside, a little cloud you can see. Basically, that's water droplets now suspended in the gas. So it's like a cloud, literally water droplets. And now as it warms up, that cloud disperses. That water is now back in the gas phase instead of little liquid drops. And it's back in where it was. And we can do it all over again. It's been very efficient here.
But we can fix that.
So again, look to see if you can see the liquid sloshing around in the bottom. Okay. Okay. And let's do another demonstration. This one, we're going to have a change of phase. I've got water in this flask here up high. And when we add the heat, well, we're going to warm up this flask. So we're going to warm up the water and warm up the gas that's inside the flask. The flask is sealed and connected to another flask with this hose, this tube. And this is just water, also at room temperature, but it's got some green food coloring added to it. So as I heat up this flask, what do you think we might observe? Anyone? So when we heat this up, would we expect the water to change its density very much, change its volume if we add a little bit of heat to it? We have to add quite a bit of heat before we start boiling it. But does the density of water change that much with temperature? How about the density of the gas? If we add the heat to the gas, the air inside this, would its volume change? Anyone? I see a couple of nodding heads. What might we observe then if we make the gas in this chamber expand? I want you to watch very closely. See what's going on over here?
Focus on the green ball.
We have bubbles. We have bubbles coming up in our green water. There's no even hint of any boiling going on over here yet in the flask that's up high, but we're making the flask and the gas inside that flask warm. So that gas is expanding. And so we see air coming out over here. As the gas expands and pushes through this tube and then out through the bottom over here into this flask. Now, once we reach the boiling point, we're going to start producing steam. Water in the gas phase is going to be coming off of this flask, and that's going to start going through the tube. Would we expect to see bubbling of that steam when it comes out? Does anyone have any comment on that? Let's give folks online a chance to respond. Go ahead and speak up and just unmute. Well, what's going to happen is we're going to start producing steam. And then once we produce large amounts of steam, that's going to push all of the air out of this flask. So eventually we reach the point where there's going to be no more air whatsoever in this flask or the tubing, because it's all going to be pushed out by the steam that's going to be produced. The gaseous water that's going to be created will displace that air and push it all out of the system. Does anyone have a prediction of what that would look like over here with the gas coming out? Once we replace the gas coming out through the green water with steam. So once that gas turns from basically hot air to hot steam. Okay, it's happened. Look, the water level is still. There are no more bubbles coming out, but this has now gotten quite noisy. You hear a lot of crackling. And if we could zoom in the bottom, we could see bubbles coming out of the bottom of the tube, but they disappear very quickly. What's going on here is we have steam coming out of this tube now. There is no more air in the system. But that steam, once it hits that cool water, condenses back into a liquid. The steam bubbles collapse and produce what's called a cavitation. We see this a lot in geysers in Yellowstone. You'll have steam bubbles form deep underground, and as they rise through the water and reach cooler water, they'll collapse. Oblong Geyser and Artemisia Geyser are famous for this cavitation. the whole ground shakes nearby. It's really cool. We were in eruption of these geysers to lie on your ground, and you could feel it's like an earthquake with all the bubbles collapsing. And you can actually look down into the pool of Artemisia and see the bubbles come up and then collapse. It's quite cool. So, as I turn this off, the water and the gas in this flask, which is all steam, all the gas is steam, it's going to start cooling down. As the gas cools down, what might we observe? Anyone? Sir?
Well, once it cools down, it's gonna lose volume and it's gonna suck some of the green water back up into the flask.
Okay, so as the gas cools down, it's going to contract, and that's going to draw water up from this flask. And we can see already, we have water coming up the tube. And the question is, how much water will come out? Will we replace the water that we boiled, or would we get more water pulled into here? Basically, how much of this flask will get full? Would it just fill just a little bit, or would it fill more than a little bit? Any thoughts? Somebody else, maybe? I can see the water level rising to about here.
From Mackenzie Robbins, more than a little.
Okay, more than a little. Does anybody want to say just a little? Okay, Mackenzie, why just a little?
Until the flasks have the same amount of liquid.
Could you say that again, please? Did you hear what she said?
She said it'll go until the flasks have the same amount of liquid, and that was Shelby Reynolds.
Okay, Miss Reynolds said that it'll go until we have the same amount of liquid in both flasks. Okay, any other thoughts? We're almost there. The water level has risen to about here. And let's see how much of that liquid we can draw. One thing to keep in mind is that this liquid is fairly cool, but the gas in here is steam, is still quite hot. And so what do you think will happen to that hot gas when all of a sudden we get a whole bunch of cold water, cooler water coming into it? It's going to contract very, very rapidly, creating even more of a pressure difference. And we've sucked entirely all the water out of the lower flask. There is no water left in the lower flask. It's all been sucked up top. That's why we call this demonstration the boiling green water sucker. Remember that initially this whole system was filled with air. All of that air was displaced and replaced with steam. At room temperature, that steam, well, it's going to condense all of it back to the liquid phase. And so we could have frankly sucked in a whole lot more liquid than we ended up doing here, because essentially all of the gas in this flask that was there before the water started pouring in turned back into a liquid and took up a lot less space. So we could have filled this all the way to the top and then even more if we allow it to overflow. Okay, so that's kind of a nice little demonstration. Now this process of phase changes, there's temperature changes going on as well. In that what's happening on the molecular scale is you have individual molecules either joining a liquid or leaving a liquid, bonding with materials, other atoms in a solid to go into the solid phase, or splitting apart to form ions in a plasma. This all results in a huge energy change for those individual molecules. And molecules are continually colliding, jostling with each other. There's in a solid vibrations. And so with just the right vibration, like what's going on in the solid carbon dioxide, through just random thermal vibrations of the material, every now and then, a molecule near the surface through those vibrations is going to get a little bit more energy than what is typical for the solid. And it's going to then have enough energy to break away and enter the gas around us. And as a result, well, you've got one of the atoms one of the molecules, in a way, you can think of it as getting more than its fair share of energy compared to all of its compatriots in the solid. And this sublimation, where it goes from the solid phase to the gas phase, is a cooling process, because you're going to be losing, on average, the more energetic, the particles that leave are going to take away more than what is the average energy of the other molecules in the solid. And the same thing with the liquid. When you have a liquid evaporating, again, the molecules in the liquid are jostling around each other, and through random collisions, odds are you're going to have molecules get a much higher average energy than what is normal, giving them enough energy to escape into the gas phase. And that means they carry away more than what is the average energy per molecule, and as a result, what's left behind is cool. Similarly, when you have condensation, when dew is forming, that's a warming process. You've got atoms in the gas phase jostling around, colliding, and through an odd circumstance, through collisions, one molecule suddenly has a lot less energy than what's typical for the molecules in the gas, so that it can join a liquid. But even though it's got a lot less energy than is what's average for the gas, it's got a whole lot more energy than what's average for the liquid. And so that will tend to warm the liquid. And so this is why when, as Hewitt points out, if you're in the shower, you step out of the shower, you feel colder because you've got water on your skin that's escaping the gas phase, leaving you cooler. But if you step back into the shower, you'll have the hot water in the gas phase condensing on you that will tend to warm you. So this brings back a memory of a canteen I had when I was in the Boy Scouts. So I got a lot of my camping gear from my grandparents when I was a Boy Scout. Now this is back in the late 60s and early 70s. And I had one of these old World War II surplus canteens with a canvas bag around it. And the canteen itself was metal. And the idea was, and my grandmother showed me this, that you had to pretty much get the canvas wet. And throughout the day, that canvas, the water on it would evaporate, cooling cooling the bag and the water that's in the canteen that's in the bag. And so all of my friends loved to get a drink of my canteen because my water was cold, while their plastic canteens were often warm and tepid. And so it makes for a great canteen to have the canvas bag that you keep wet. And as a kind of a demonstration of this, I have two thermometers. They're both mercury thermometers. And this is an antique. And they're both measuring, oh gosh, it's in Fahrenheit, 74 degrees. And I don't even think it'll show up on the camera. But could I get an observer to come down here and verify that both of these thermometers are reading 74 degrees? Just another pair of eyes. Or we could probably trust Colton. Colton, can you read those? Both of them?
Where am I reading it at? Right
Where the mercury is. The end of the mercury.
10?
No, it's not 10 degrees. Look out over here. You see the mercury? It's a silver line in the center. So where does the silver line end?
Looks like 74.
Okay, how about on this one? Where's the mercury line end?
74.
Okay, so both at 74. But on the end of this top thermometer, there's a little bit of a cloth baggie. I'm going to get that wet, and the water's at room temperature, so that really shouldn't change anything, but we will get evaporation of that water, especially if I spin it around and get some convection going. So we should get some evaporation off of that baggie, and this evaporation, the water molecules escape to the gas phase are going to take away more than what is the average energy of the water molecules, and that's a cooling process. So even after this short time, we should see a noticeable temperature difference. And so, Colton, what's the temperature of the lower one?
A 73.
73. How about the top one? It's over here.
$69.
Yeah, right around 69. It was colder earlier, but it's starting to warm up. But that's this evaporative cooling. And as another illustration, I've got the classic drinking bird here. And this works because as the bird dips his head, it gets his head wet. And then we're going to get cooling of the bird because the water that's in on this felt that's on its head is we're going to start to get evaporation going on. Oh, come on.
Yeah. It's doing the demo without the vacuum chamber lid.
Okay, but in this chamber, it's partially evacuated and there's a green alcohol in there. And so we have, as the alcohol gas is cooled, it wants to contract, and that changes.
Doesn't seem to work when you do in the pool, but it was working fine before.
Yeah, that's the problem. Okay, if we have them just out here, away from the water, the reason I have the water down, well, there's a reason I have the water. So basically we have water evaporating off of the felt head, that's cooling the gas, and that's contracting the alcohol vapor. As the alcohol vapor contracts, it draws the alcohol, more of it up to the bulb that's in his head, making his head heavier so it dips down. And as soon as his head touches that water, his head is then warmed because the water's at room temperature. And the gas then quickly expands, pushing the liquid more down towards the bottom. And so he drinks. As once he gets up, the alcohol in his head is cooled by evaporation, and to the point where the alcohol is drawn up into his head and makes it heavier and it tips over. And as soon as his head touches the liquid, the alcohol vapor is warm because the water's at room temperature. And then it bobs it back up, and then we have cooling going on again. But the drinking bird is a social drinker. So if we put him off by himself in a room, he stops.
I think partially because I can't.
Well, let's move him so we can. And this is kind of a joke, but the reason he stops is because once the gas inside the chamber gets saturated with water, the humidity rises. He's no longer going to be able to cool by having that liquid evaporate. In fact, he stopped. It's not that he's hitting one of the side walls, he's just stopped because we're not getting that alcohol cooled anymore because we're not getting the evaporative cooling because the humidity is really hot. So basically, one of our best cooling mechanisms is evaporation of sweat off of our bodies. But if it's really, really humid, that water off our skin is not going to want to evaporate, and so we don't get that cooling effect. So that's why the bird stops when I put the chamber around him. And he should start again, especially if I move him away from all that moist air where we had the pool of water that he was sitting in. Okay, that's kind of a nice little demonstration.
On their CO2 balloon.
Oh, where is the CO2 balloon?
The lucky one right
Okay.
there that
We still have some carbon dioxide in here, but you can see that we have quite a bit more gas than we did before. So again, to illustrate the huge difference in volume we get between a solid and a gas.
So once that pressure gets high enough in the balloon, will it stop evaporating?
No, it's going to continue until all that solids turn into a liquid. And so I mentioned that we're cooled. We rely on sweat to cool our bodies. So of all the three processes by which heat can be transferred, convection, conduction, and radiation, well, convection is what's going on here. So when something evaporates or condenses, that's convection. You have physical motion of material going on. Water is leaving your skin and going into the air. But also, more importantly, we rely on our blood to take heat away from our internal organs and through our capillaries transfer that energy to our skin, where then we can get radiation, but mostly, again, convection. Either we're directly warming the air that's in contact with our skin and it's taking the heat away from us, or we're having evaporation off of our skin. So of all the processes of heat transfer, convection is by far the most important in our regulation of internal temperature. And that's about all we can talk about today. We'll talk a bit more about phase changes then on Friday. Thank you for your attention. I got through all the demonstrations.
Except for the cocaine crush.
I did do that.
Oh, I've
Do you
seen
want
that
that
trick before.
I
Friday
think we
or?
could probably skip on the cocaine crush.
Okay.
This one.
I think the one